All right, and welcome to the lesson 1.4 solving linear systems notes. We'll do a quick review of some two variable systems, which you hopefully would have seen in a previous algebra class, but today focuses mainly on three variable systems of solving. So, and then at the end we'll look at a situational deal, kind of the word problem or the real life problems involving three variables. So, I think let's just jump in and get it done. All right, so here's a quick review of what you would have seen in a previous algebra class where you were solving a system of equations. Remember, a system of equations involves multiple, here, linear equations. We're solving linear equations in two variables, two or more linear equations in the same um, coordinate plane, or part of the same situation. So when we're asked to solve this system, hopefully we've heard of a method. There's a couple different methods. We'll look at substitution here to start. When we're looking to solve a system of equations, we are looking for an ordered pair that satisfies both equations. Okay, so in the end, we're looking for what point, an x and a y coordinate makes both of these equations true. Because we could sit here and kind of come up with a lot of different y values, times 4 minus 1 and get x values, but only one combination of x's and y's is going to work here as well. So let's get into it. That's kind of what a solution is. Let's look at how we find it. So using substitution, this is a good candidate for a substitution because it has a variable all by itself, isolated on one side of an equation. This x is flying solo on the left side of that second equation. So that's what makes this a good candidate for substitution. If that weren't the case, we could pick one of the four variables, right? I've got an x and a y in this top equation, and I've got an x and a y in the bottom equation. If this one wasn't here by itself, like let's see here, like this, we could pick one of the four and try to get it by itself, which is, in this case, I'd probably move the 3x to the other side. We'll get to that one, but the reason I might want to use substitution is because an equation is already set up for that. Okay, so that's kind of a little bit as to why we might want to use substitution. So let's go through that actual process. To use substitution, we actually substitute. So whatever x is equal to, right now I know x is equal to 4y minus 1. I'm going to take that expression and replace x with it in the first equation because I know x and 4y minus 1 are the same thing. We were told that they were equal. So I'm going to replace, I'm keeping this 2 the same. I'm going to replace that x with this whole expression, 4y minus 1. I'm going to keep the plus where it is. I'm going to keep the 2y where it is. And I'm going to keep the equals 3 exactly where it is. All right. So all I've done is substitute an x with an expression that I knew x was equal to. From there, we're done. The advantage to doing that is we've got an equation here that only has one variable in it. So we can solve it. We can figure out what value of y makes this true. So I've got a little bit of distributive property get going on here, 8y minus 2. All right, I'll combine some like terms here, 10y. I'll add a 2 to both sides. I know I'm running out of space. And then I'll divide both sides by 10 to get y equals 5 over 10, or 1/2. Okay, you can say 1 over 2, 0.5. I'm okay with that, either one. So what did we just find? We found half of our solution, of our ordered pair that we said, okay, hey, the y value that works here, if I plug in a 1/2, what happens? Times 4 is 2, 2 minus 1. I get, well, I'd kind of just finished it for us there, but that's how we're going to figure out what x is. All right, we got to figure out, okay, what's the x value now? So I kind of verbally went through it there, but let's take a look. How am I going to find the x value? I'm going to take what we just figured out y was and go back to either one. Now, this one's probably set up the nicest because it's got this x already by itself. So I'm going to take this y equal to 1/2, and on this lower equation say, all right, x is equal to 4 times y, which we now know is 1/2, and subtract 1. So 4 times 1/2 we said was 2, and then 2 minus 1 is 1. So x equals 1. So the point 1/1/2 ends up being our solution. The check, it doesn't even have to be like a big formal check or anything like that. if I want to guarantee and I want to know this solution is the actual true solution to this system of equations, I could substitute the 1 and the 1/2 in for x and y. So 2 times 1 is 2. 2 times 1/2 is 1, and then 2 plus 1 is 3. If that ends up being true, I know my solution is what it should be. The other thing to also note here, what did we actually find? Besides just a point that works in both, it's the point. These are both lines. If I were to graph this, we'd see it was a line. We'd graph this and see it's a line. We would see that the point that these two lines intersect is right here. All right, so on a couple different levels, including graphs, ordered pairs, solutions, that's what we're finding when we're finding a solution to a system of equations. All right, let's look at a different method. All right, we'll scroll down here. So the other method, the other most common method is elimination. What I need to do for this one, I'm going to eliminate a variable. So not substitute. We talked about how we could substitute on this one. Let's use elimination. So the first thing we'd want to do is make sure everything's lined up. I want my x's above x's, which we don't have. I want my y's above y's, which we got to fix. Equals above equals, and constant above constant. So we got a little bit of rearranging here to do. Not a ton. I basically need to get my 2y and my negative 4x rearranged. So I'm just going to, I'm just going to bring this over here to keep this 3x plus y equals 1, exactly how it was. But I need to bring my minus 4x out to the front. Remember, this minus is attached to that 4x. And then that 2y is positive, so it should read as plus 2y equals negative 68. All right, so just a little bit of a rearrange there on that bottom equation to get my x's above x's, y's above y's, equals above equals, and constants above constants. All right, so from here, we want to eliminate a variable through addition. So right now, if I were to add these, what's going to happen? 3x plus negative 4x is negative 1x. 1y plus 2y is 3y. And 1 plus negative 68 is negative 67. Well, I didn't help myself out much because I'm still left with something that has an x and a y that I can't solve for. There's an infinite amount of solutions here, combinations for this. So I need a different strategy. We will add them like that eventually. I don't want to take too much off here. But I need to get opposite coefficients on either one of the variables. All right, so I could look at the x's and say, you know what? I could multiply this top equation by 4 and get a 12 here. I could multiply the bottom equation by 3 and get a negative 12 here. I could look at the y's and say, you know what? I could multiply this top equation by negative 2, and then I'd have a negative 2 and a 2, and then I could add and I would eliminate the y's. So that's what I think I'm going to do. The key part of this is we need to multiply this entire equation by whatever we're deciding to multiply by. So we're deciding to multiply by negative 2. I need to multiply all the pieces. So we'll do our work. We'll bring this one down here. Negative 2 times 3x is negative 6x. Let's come on over here. Negative 2 times y is negative 2y. And then we'll come all the way over here, even to the constant. So I need to say is equal to negative 2. All right, so everything got multiplied by negative 2. The bottom, I'm just going to kind of leave it. There's a second equation here. We're just going to leave everything as it is. So negative 4x, positive 2y, negative 68. But now, when I go to add them up, what's going to happen? Negative 6x plus negative 4x is negative 10x. Negative 2y plus 2y disappears. That's the elimination portion of this. And then negative 2 plus negative 68 is negative 70. All right, the finish then is very similar to what we did up above. Is I'm down to this one variable. We're going to solve it using some of our traditional methods as, all right, let's divide both sides by negative 10 and say, hey, you know what? I know what x is. X equals 7. Negative 70 divided by 10 is 7. So it's kind of like before, is now I know half my answer. It's the same idea. We're going to write our solution as an ordered pair. So 7, how am I going to find my y? Same process. Go back to either one of your two equations and plug this value 7 in for x. So I guess I'll come up to this top one. The numbers look a little bit smaller here. I'm going to go 3 times x, which I know is 7. And then I'm going to say plus y equals 1. So we've got 21 plus y equals 1. We'll subtract a 21 from both sides to say that, or to find that y equals negative 20. So there's my solution. Again, a quick confirmation. I can do this even just in my head if I wanted to try to just a quick check. 2 times negative 20 is negative 40. 7 times 4 is 28. So negative 40, or what do we got here? Negative 40 minus 28, yeah, is negative 68. Maybe I should have wrote some of it down. So yeah, it checks out for us. I think we're okay. I think the first one we found, we used it correctly. So that's a review of 2 variable systems. You say, oh my gosh, that's just a review. The nice part about 3 variable system, which is what we're looking at today, there's no new strategy. There's no like, all right, hey, use substitution, use elimination, or some weird new strategy. It's essentially going to use either one of those processes, but maybe just a little bit more of them within a given problem, okay? So just a very, very brief kind of notes. What are the potential outcomes here? We looked at 2, before we get too far into it, we looked at 2 examples that we ended up with a single solution, right? We got this 0.1, 1/2. We got this 0.7, negative 20. We got a solution. That's one possible outcome. So with a 3 variable system, that would be kind of our quote unquote normal outcome where we end up with just one solution. We'll write it as what's called an ordered triple. So now we would have an x coordinate. Let's do it like this. We'd have an x coordinate, a y coordinate, like an ordered pair, but there's going to be a third unknown. We'll write it as what's called an ordered triple. All right, so an x, y, and now a z. The other situations that we haven't looked at yet, we will, are a potential no solution and a potential infinitely many solutions. All right, so what ends up happening, just very briefly, I know you can kind of read, the variables disappear, but we'll end up with a false equation. So what an example of what that might look like is, let's say I go to eliminate my x's, and I need opposite signs on these. So let's say I ended up with negative 2x and then a 2x in my second one. But even with whether I realize it or not, I ended up with opposite signs on both the x and y, or opposite coefficients on both the x and the y terms. So when I add this left side of the equation, I'm going to get 0. That whole side disappeared. Now the right side, depending on what these numbers are, could be it could be anything, 10 and 5. When I add there, I get 15. This is how I know that there's no solution to this system. I got a statement that was false, that 0 equals 15, and we know that's not true. 0 doesn't equal 15. 0 equals 0. 15 equals 15. So when that happens, I finish up and I just say, hey, this system has no solution. So we'll look at how that whole situation plays out kind of from the beginning. That for infinitely many solutions, not much would be different. I'd end up, we can even keep those same numbers. 2x plus y equals 10. And then let's say that through the course of solving the problem, I ended up with 2x minus y equals negative 10. So I get opposite numbers on every coefficient. Eliminate. So I still have a 0 over here. But now instead of a 5, I end up with 10 and negative 10. I get 0. So everything eliminated. 0 equals 0. That's how I know that this has infinitely, and this is what I'd want you to say, infinitely many solutions. All right, so we'll look at an example of how that happens or what that looks like, okay? So I think other than just kind of jumping in and looking at, okay, how do we actually do this? We're going to kind of go through those same 2, elimination and substitution, just as they come up. So here we go. Example 1, use the elimination method. I'm not going to say you have to use one or another. I think this is a really good candidate for elimination. Why? Because my x's are lined up, my y's are lined up, my z's are lined up, equals, and the numbers, the constants, okay? So that's, you kind of just evaluate or just assess the system and see, okay, hey, you know what, this one's a good candidate because everything's lined up that way we would want for elimination. All right, so here's the deal. You pick any variable that you'd like to eliminate. All right, so as I'm kind of scanning it here, I'm looking for maybe some good candidates. I see the x's right now. I see a negative x and a positive x and think, you know what? I could add this equation 2 and equation 3 just how they are, and I could eliminate the x's. Do I have to? No. I could decide to, hey, you know what? Why don't we multiply this bottom one by 2, and I could get a negative 4z, and I'd have this 4z, and I could work with the first and the third one. So you pick any combination of equations and any variable and eliminate it however we can. All right, so let's go with that first one that I mentioned. I'm just actually going to draw a line right here and say, you know what? I didn't even have to touch this equation and this equation. I can add them exactly how they are and go negative x plus x, 0, eliminated. I'll probably want to keep that there because I think I want to see these at some point. So the x is eliminated, but we're going to add up the 5y plus 3y, which is 8y, 12z minus 2z or plus negative 2z is 10z, and then 73 plus 1 is 74. And what I like to do is just put a box around it. Now here's the downfall is I still have two, whoops, I lost my z there. I still have two variables left. I didn't until I add this back in there. So I can't just finish this and say, wow, that was easy. I have two variables still. I say, okay, now what? Well, we've decided to eliminate x, right? We said, you know what, those x's were awesome. They were lined up. We got rid of them. I need to now, once I've kind of chosen a variable to eliminate, I need to eliminate that same variable but using a different combination. We went with 2 and 3. I can go with either 1 and 3 or 1 and 2. So I got to pick here. I'm going to go with 1 and 2 and 1 and 2 and eliminate my x's that way. So here's what I'm seeing. I'm seeing this. I'm going to rewrite this one all the way over here. I'm going to say 3x minus 2y plus 4z equals 20. So I didn't touch that top one, what we're calling equation 1. And I'm seeing here on this one, if I can multiply this everything, all 4 pieces by 3, what's that going to do for us? Well, right here, we're going to end up with negative 3x, and you can already see, like, hey, what's going to happen? All right, those x's are going to eliminate, and we said that's what we got to do. We eliminated the x's once. We got to do it again. Just don't forget, and it's really easy to miss and lose track of signs, so stay super organized. That's kind of the key to these problems. So I'm going to end up with a 15y. I'm going to come all the way over here and go 36, positive 36z, and then one more time all the way over to here even. Let's see, 73, let's double check it. 73 times 3 is 219. Big numbers, so what? It is what it is. All right, so when I go to add these up, we kind of already said we picked that for a reason. We're going to eliminate here. We're going to end up with 13y. Let's see, we're going to end up with, I can read my own writing, 40z, and then 239. Put a box around it. All right. Okay, still, I haven't eliminated anything. We still got 2 variables. But right now, at this point, we're essentially starting where we started this problem. There was 2 unknowns, an x and a y and an x and a y. Both had equations. What did we do? We lined them up and eliminated. We're starting at this point, after doing a pretty decent amount of work, with 2 equations that have a y and a z and a y and a z. We need to eliminate something. All right, and we'll be able to solve for the one that's remaining. So I'm kind of looking at the numbers here. What would be good to eliminate? I don't like the y, this 8 and this 13. Just big. I mean, could we eliminate them? Sure. I think the easier elimination is going to be, let's take this equation right here and multiply it by negative 4y. Let's see what happens. Negative 4 times 8 is negative 32y. I'm going to go 10z times negative 4, which is negative 40z. And then I can come all the way over here and multiply this 74 times negative 4 and get negative 296. And the reason I'm doing that is because this one, if I just drop it as it is, I'm going to have a 13y. I'm going to have a 40z, this positive 40z. Oh, there it is. If you didn't see it yet, hopefully we're seeing it now. And then positive 239. So I didn't have to do anything to this second one. Does it always work out that way? No, potentially I might have to multiply this equation by something to get a lineup of my coefficients. It just so worked out where I was able to just keep that one as is. So here we go. Finally, we're going to be able to eliminate something. So let's go negative 32 plus 13, which is negative 19y. Our z's will eliminate. We'll go negative 296 plus 239 and get negative 57, and we're holding our breath here. If we divide by negative 19, we're hoping we're going to get a decent number. So I think for the sake of this lesson, I've tried to keep all the numbers where they're working out to integer solutions, although we just looked at one where there was 1/2, on one of the two variable ones. But I think for the most part, I have these ending up as integer solutions, just so we can kind of get a feel for. There's almost like a built-in check there for that one. So I've got one of my three numbers that I'm looking for, and you're like, wow, that's a lot of work just to get that one number. All right, we've got y equal to 3, so I'll put it in the y position. Remember x, y, and z. So I'll put that in my y position. Believe it or not, we're almost done. Yeah, right. Because I've got two equations now right here and right here where I can just take this y and plug it back in and solve for, in this case, z. All right, so the rest is just substitution. Let's see if I can squeeze this in here. So 8 times y, I'm going to kind of do it as I plug it in because I'm running out of room. So I'm taking this 3 that I just figured out what y was equal to and plugging it in for y. So 8 times 3 is 24 plus 10z is equal to 74. All right, so I did that multiplication. I don't always like to do that, but I'm just kind of getting tight on space here. So I'll subtract that 24 from both sides to get 10z equals, what do we got, 50? And then divide by 10 to get z equals 5. All right, so my z position looks like 5. If I have any room left, let's go. I guess I can always erase, and now that the work is done, we can scroll up. So I'm going to have to go, now I'm going to take this z that we know, value of 5, this y value of 3, and then I can go back to any one of the 3 original equations, plug those numbers in, and solve for x. I'll go to that bottom one there. So go x plus 3y plus 3 times 3. And then let's see, we'll go minus 2 times z, which we're saying is 5. And that should hopefully all come out to equal 1. All right, I picked that one again just kind of because the numbers were small. You could have went into any one of the 3 equations. So x plus 9 minus 10, if I can read my writing here, x minus 1 equals 1. And we'll add a 1 to both sides and get x equals 2. So I think we're in pretty good shape there. The numbers did all work out. Now, I guess I don't necessarily, that doesn't guarantee that my answers are correct. Could I check these? Absolutely. I could 100% take these numbers and plug them in here for x, y, and z, plug them in here for x, y, and z, and hopefully they would check out. I think we've got the numbers that we were looking for. So that's the process, and you're looking at the final result, and you're like, oh my goodness. It was a process for sure. It was ended up being 3 eliminations kind of within one given problem. So versus a 2 variable was we got to just do that once and be done. That's kind of how we have to do it. So like I said earlier, stay organized. Come up with a system that works for you. Spread your work out. Don't try to plug stuff in, and work right on top of the original equations, because you're going to lose track of a minus sign, and that's all it takes is losing track of one little teeny tiny sign somewhere along the way, and the whole problem may not work out. All right, a couple more here. So let's take a look at what does it mean, and we can see what's going to happen. We kind of know what's going to happen. We're going to end up with a no solution, but let's see, like, how do I know that's going to happen? So off the get-go, you kind of look at it and you see, this one doesn't look much different than the one we just did, right? There's x's, y's, z's all lined up, a bunch of numbers. So other than this right here saying, oh, hey, there's a no solution. Now, I'm not going to be that nice. I probably wouldn't tell you that. We got to figure that out. So I'm looking at the variables. I kind of start to see, hey, I got y's, a 4y and a y that I could eliminate. That's kind of it as far as right off the bat. Here's the other thing. Here's a little bit of just kind of an inside look at it. I'm looking at these top two equations. So the first one and the second equation, and I'm starting to kind of see that. All right, 1x and 2x, 2y and 4y, 5z and 10z. What's true about all three of these coefficients in that top equation? They're all exactly twice as big as the coefficients in the second one. So I'm kind of leaning towards, you know what? Why don't we try something here? Why don't I keep this top equation exactly how it is, 2x plus 4y plus 10z equals 14. And then I'm going to take this second one and multiply everything, all four terms, by -2. So whether I saw that initially, and I kind of was leaning there a little bit because I'm cheating and I know there's a no solution, but I see that and say, hey, wait a minute. If I multiply this out here, I'm going to get -2x. I'm going to get -4y. I'm going to get -10z. And I'm going to get +8. So it's kind of that what we had talked about with the notes portion of what's going to go on here. Well, eliminated. I still have a 0 there. 14 plus 8 is 22. That's not true, right? That's a false statement. As soon as I hit that mark, I am absolutely done, and I say there is no solution. So these ones are kind of nice in the sense that once that happens, it's over. I don't have to go through 3 different eliminations. Now, what does that always happen on the first one? Absolutely not. We talked about, at least I had mentioned earlier on. So this problem's over. It's no solution. But I wanted you to at least hear and see that doesn't always happen right away. Like we kind of strategically picked these two to work with because, I could kind of see what was going to happen there. I think a lot of people's first reaction would have been to this 4y and this -4y to add up. Those would have eliminated. We would have had a 5z a 5x with the x's, a 7z, and 29 had I added those up. So we would have had to keep going. But at some point, whether it was the first elimination like we did, this is our first one. Let's go back and just reference here. Whether it was the first elimination, the second elimination, or the third elimination, which was right here, at some point, if it's a no solution or an infinite solution, you're going to end up with kind of that nonsense statement there like that. All right, we lucked out. We picked a convenient one. It doesn't always happen that way. It might just kind of show up mid-problem. Let's maybe try to get that to happen with our infinitely many solutions, okay? So this one's got a lot of, again, we've got many solutions here. I see 2's, 2x, 4x, 4x. So there's a lot of similarity, 12, 6's. So I'm thinking, all right, well, let's start eliminating. So I see this right here. I say, you know what? This 2y and this -2y are going to go away right away. So why don't I just add them up how they are? What's 4x plus 4x? 8x. What's 2y plus -2y? Gone, eliminated. And 8z plus 8z is 16z. And then 12 plus 12 is 24. So you can see, I was thinking maybe I was going to hit it right away. And wow, look at that. I'm done. But hey, you know what? We ended up with 8x plus 16z. So I just keep going. I got to all right, that's how that one worked out. I eliminated. It is what it is. All right, we've eliminated our y's. Let's eliminate our y's a different way now. Now I'm gonna go with these top two because I'm also seeing a -2y and a 2y just how they are. So I'm gonna add the top two exactly how they are. All right, so 2x plus 4x is 6x. -2y plus 2y is gone. Those will eliminate. 4z plus 8z is 12z. And then 6 plus 12 is 18. All right, second elimination down. So far it's like, oh, okay. What's going on here? Now, how am I going to get these to eliminate? All right, the x's aren't nice numbers. These aren't nice numbers here. I'm seeing this 6 and this 8 and recognizing, hey, those both go into 24. So let's get it to eliminate that way. I'm going to take this top one here, or this left one, I guess, and multiply it by -4. So times -4. So 6 times -4 is -24x. 12 times negative 4 is negative 48z. And then 18, I think that's an 18 if I can read my writing. 18 times negative 4 is negative 72. Now to get this one to line up, I'm going to need to multiply everything by 3. So times 3. 8, I'm going right here. 8x times 3 is 24x. 16 times 3 is positive 48z. And then 24 times 3 is positive 72. And I'm thinking, oh man, if only I would have hit this earlier. Eliminated. So I got a 0 on this side, and then negative 72 and positive 72 is eliminated. So 0 equals 0. That's a true statement. So this is where I would follow up and say infinitely many solutions. So you can see, it was just kind of the bad luck, I guess, that I picked the combination of variables and equations to work with that I did an elimination. It looked like it was going to work. Did another elimination. It looked like it was going to work. And I'm saying, finally, okay, let's eliminate something. And by that third one, I hit it. All right. So you never know necessarily as far as how it's going to go. But at some point, that should happen if it's an infinitely many solutions. All right, we're almost done here. Let's finish up. We've got one more. I do want to just show one that it is still possible to solve a system using substitution. And again, I think this one is a good candidate for substitution for the same reason as it was with our two variable one. It's already set up that I've got a variable right here isolated. I've got y equal to x plus z. So what do? I say, all right, I'm going to go up to the other two equations and replace that y with something that it's equal to. So let's start with that one. So 2x, I'm copying down this 2x. I'm going to replace that y with this whole expression. So basically x plus z. So plus, I'm copying down that plus. Now I'm replacing my y, x plus z. And then plus this z that's already there equals 8. So I've substituted. All right, a little bit of simplify, not terrible. 2x plus 1x is 3x. So I'm combining that and that. I've got z plus z, which is 2z. And then I've got my 8. All right, fair enough. Done. Second substitution coming right here. I'm going to take this now and do the exact same thing on this equation. Let's keep this opposite of x. So opposite of x. Where can we squeeze it in? Try to line it up. Opposite of x plus 3 times, but now instead of y, we're going to say x plus z because that's what x, or that's what y is equal to, minus 2z, and then equal to 3. All right, so I kept everything the same except this y right there. Replaced it. All right, a little bit of distributive. So I've got my opposite of x plus 3x plus 3z minus 2z equals 3. Too many 2's and 3's here. My z's and 2's all start to look alike after a while. So let's combine like we did in the last one. So negative x plus 3x is 2x. We've got a 3z and a negative 2z, so that's 1z, and equal to 3. So I'm going to box it. That's just kind of a Mr. Kroll special there, where once I get down to two variables, I box them up. From here, there's no magic formula for substitution. I could use substitution one more time here with this one and get the z by itself if I was really feeling in the substitution mode. I'm kind of seeing this as, you know what, I've got a 2z here. If I multiply this whole equation by negative 2, I can get a negative here. So kind of a combination of substitution, and then I'm still going to use elimination to finish it up. All right, I can get a negative 2 there and get these z's to eliminate. All right. So let's do it. Let's keep this one as is. 3x plus 2z equals 8. As I bring this one over, this is just a note to myself to make sure I don't forget. Let's multiply everything by negative 2. What's going to happen? Negative 4x, negative 2z, and then negative 6. So I still end up using elimination. Kind of nice here. I got negative x, or the opposite of x. Eliminated the z's, equals positive 2. Divide both sides by negative 1 or multiply by negative 1 to get x equals negative 2. Awesome. Everything else is set up just how we did earlier. So I've got an x equal to -2. Why don't we come right over here? I'm going to plug it into one of these two. I could come here. If I could also come there if I wanted to, because they're down to x's and z's, x's and z's. I'm going to plug this in. We'll do the same as before. 2 times -2, which is -4, plus z equals 3. We'll add a 4 to both sides to get z equals 7 and say done. Last but not least, one more time. Again, great candidate right here to plug in that x and that z that we just found, because it's set up just to spit out a y. So y equals x, which we're saying is -2, plus z, which we're saying is 7. So I just got one last calculation here. -2 plus 7, which is 5. So if I finish this up the way we should say that the point -2, 5, and 7 is my ordered triple. That's my solution. So we finish it up right there. So a good example of, you don't have to always use elimination. I think for a lot of us, that's probably the easiest one to latch onto, but I think it illustrates that substitution could actually maybe speed up the process. This one didn't have a number in it, right? Y equals x plus 7, or I'm sorry, not plus, y equals x plus z, which ended up being 7, but if I wanted to use elimination, I would bring this x over. You'd have a negative, an opposite of x. I'd line this y up here, plus y. I'd subtract a z, so I'd have a negative z, and then equal to 0. So you could still solve that using elimination. You would just be equal to 0. All right, last one. Let's get to that. I think we can definitely check off our solve systems in 3 variables algebraically. We looked at it several methods: 2 variable, 3 variable, elimination, substitution, no solution, infinite solutions. Let's just look at one real life kind of situational one. The part here is what I think makes all word problems tougher is that each one is unique and each one has their own type of setup. I think for this particular one, there are some commonalities though. So I mean, I guess we'll go through a process that we can hopefully transfer to other 3 variable systems. So let's read it. An amphitheater is charging $75 for each seat in section A, so up close to the stage, $75. $55 for seats in section B, and then $30 for each lawn seat. Okay, so that's, I think, a very relatable situation. Tells us there's 3 times as many seats in section B as in A, which again, I think picture-wise kind of makes sense. You're going to be able to fit more seats here. So they're telling us there's exactly 3 times as many seats in B than there is in A. And then if we sell all 23,000 seats, so apparently this venue seats 23,000 people. If we sell all those seats, the revenue is $870,000. All right. With that, based on that information, we should hopefully be able to answer how many seats are in each individual section of this concert venue, or this amphitheater. Wow. All right, let's do it. I'm probably need a little space to work here. So I think now that we've seen the picture, maybe I'll take this out of here just because we know what's going on. Hopefully we have an idea, just to give me some space to work. So we need, first things first, we're going to define our variables. So what does that mean? Whatever you want to use for your variables, capital letters, lowercase letters. I think for a problem like this, where it's kind of saying, hey, there's an A section, there's a B section, and then a lawn section. In my head, it makes sense to say, let's call our variables A, B, and L. Why capital? Well, I know a lowercase l looks like a 1, so I'd just rather keep them capital, I think. It doesn't matter. And what are those? So A is going to be the quantity. I'm going to use number sign, the number of section A. Whoops, if I can spell right. Section A seats. Section, oh boy. Section A seats. Okay. B would represent the number of section B seats. And then L I'm going to use to represent the quantity, the number of lawn seats. All right. So I want you to do the same. I want you to have a spot where you define, because you might choose to use X, Y, and Z for this equation or for this situation. So we would obviously want to make sure that you finish the problem knowing, okay, I figured out what X was, but what the heck was that? Was that B or was that lawn seats? So it's almost it's as much as a note for you as it is your reader to know at the end, like, hey, this is what I found. The other huge thing we need here is we need 3 different ways to relate these pieces of information, or not these pieces of information, but these unknowns. How are 3 different ways that these are related? And I think we've got them here. I've got a total cost situation where there's a $30, $75, $55, and we're spending $870,000 total. I think there's a spot that says there's 3 times as many seats in section B as A. And then I know that there's a total, here's a third piece, there's a total quantity of 23,000. So of 23,000 seats. So it doesn't necessarily matter what order we set these up in, but I think that's the information we're going to use. So if these are all, let's start with the 23, because I think that's the most maybe intuitive one to look at. That if I take the number of A seats, however many there are, I have no clue, it's unknown, and add that to the number of B seats, all right, again, it's also unknown, that we're going to and add that to the number of lawn seats, there are 20, that should add up to 23,000 seats. All right. Now we've used that. We're not going to use that information again. Like, that's out of the picture. I don't think we have to use that again. Let's do the cost one, because I think that's also a fairly intuitive equation to set up. All right, if they charge us $75 for however many A seats there are, and I add that to $55, maybe I should switch colors here and line it up with what I underlined. So if I charge $75 for every A seat, add that to $55 that we're getting for every B seat, and $30 for every lawn seat, that should come out to, I'm going to slide this whole thing over here, so just give me 1 second, because I know I'm running out of space. If I can grab this, maybe. No. Oh, there we go. Oh, I didn't want that A. Sorry. Let's just slide this over, because I know that 870 is going to be tough to squeeze in there. We should come out to a total, when I add all those costs up, times per each ticket, we should come out to $870,000. So that's like a revenue equation. All right, we take into account all the costs per ticket, and we looked at the total costs that we're bringing in, the total revenue. All right, lastly, I got to get to my pink marker here. This piece of information that there's 3 times as many seats in B as A. Okay, and that's all I need. I just need a way to relate the different variables. So the question with this one, and what you'll see, and I'm going to write it actually both ways. Okay, so 3, if I just read it as is, 3 times as many seats in B as section A. That's how a lot of people take that and say 3 times the B seats equals A. I'm going to pose this question. Why not 3 times A equals B? It's one of those two. Which one is it? And this is a spot that a lot of people will actually get backwards, just because of the way it's written, I think. 3 times B, A. Okay, so B3B equals A. What do I have more of? Are there more B seats or more A seats? It says there's 3 times as many B seats. So I actually have more B seats. So the way this should work out is, if I take the number of, if I look here and say, okay, however many A seats we have, I have no clue how many there are, but if I take that number and triple it, multiply that number by 3, that's going to be equal to the number of B seats. And so I think this is where we want to be, versus here that says, okay, hey, take the number of B seats, triple it, and that'll tell you the A. That's going to be way too much. It's backwards. Okay, so I'd encourage you to even write that out like that, just to kind of see it and talk yourself through it a little bit. So I'll do that. Maybe I'll just rewrite it. 3A equals B ends up being my third equation. So I need to come up with 3 different equations relating our unknowns. It doesn't have to involve them all. Here, I didn't say anything about the L's. So that's how we would set it up. From here, it solved the system. It's right back to what we had done earlier. Obviously, we've created, and there's a little bit more work going on there as far as defining the variables, you coming up with the actual system itself. But from here on out, it's solve it how you want to solve it. I see this one like our last example, actually, that I kind of want to use substitution. I see this 3a equals b and just say, hey, you know what? I'm going to get rid of this b here and substitute this 3a in to this top equation. So this is going to look like this. If I start, so now this is the last part, the solve part of it. I'm going to replace this b right here with this 3a. So a, I'm just copying down this a, plus, but instead of b, we're going to say 3a plus L equals 23,000. All right, so 3a plus a is 4a, and then I'm going to leave it just like that. The reason I like the substitution, I'd encourage you at least to try it once in a while. I see just a lot of people always just kind of get locked onto one method. That was nice. Like, that didn't take much to get us down to two variables. And we're going to do the exact same thing here. I'm going to replace this b with 3a. So everything else is going to stay put. I'm going to keep the 75a. Let's try it up here. 75a. Now we're still going to have to distribute and everything. So 75a plus 55, but instead of times b, it's going to be times 3a plus 30L. Ooh, and we're going to be tight on space here. 870,000. Is that all right? So 50, I'm just hitting this on the calculator. 55 times 3, just so I have that number. So 75a, whoops, yeah, go ahead, plus 165a, I just didn't want to forget about it and write it down, is still equal to that 870,000. All right, let's combine our like terms here. So 165a plus 75a is 240a plus 30L equals 870,000. Box it, you know me, that's what I'm going to do. I'm down to two variables, that's what I got. Whew. All right, are we done? Not quite, but we're getting there. We're pretty close here. I know I'm scrolling. I see this. Let's use elimination now, just like we did again with that substitution example. I'm going to take this equation and multiply by negative 30 because I know I can get those L's to disappear if I get a negative 30 right here. So let's keep this one as is. Well, whatever. Let's bring this one down. We said we're going to multiply times, what did we say? I already forgot. Negative 30. So I'm going to end up with negative 120a minus 30L. Need a little help on this one. 23,000 times negative 30 is negative 690,000. And then we can bring this one exactly as it is, 240a plus 30L plus or equal to positive 870,000. Numbers getting big, but watch this. Here we go. Gone, eliminated, right? This is just twice as big, so we're talking 120a being equal to 180,000. We'll divide both sides by 120 to get a equals 1,500. Now, is that it's one of my answers, and that's where using the variable is nice. I do have my kind of cheat sheet that to remind me what it was, but I picked nice variables to remind myself that, hey, you know what? We just figured out that section A has 1,500 seats. All right, so I do have to kind of scroll up here, I guess, so I can kind of see both. I'm going to plug that in. Let's figure out the B right away. So 3, I just basically need to triple that. So the B seats, I think we can do it right here. B is going to be equal to 3 times that number we just came up with. So B equals 4,500. So far, so good. We've met that criteria of B is twice as big as A, the quantity of seats. All right. And then what did we say? When we add everything together, A plus B plus the lawn seats, we should be at 23,000. So I think I can remember that. Let's try it right down here. Let's go the number of A seats plus the number of B seats plus the number of L seats should come out to 23,000 total seats. So we've got 6,000 between these combined. All right, we'll subtract it, and hopefully that's it for our lawn seats. So 23,000 minus 6,000. I should do that without a calculator. 17,000. All right, so let's bring it up. Let's kind of wrap pretty little bow around this one. A equals B equals L equals. We do want to finish it and kind of say, all right, how many seats in each section? This is where our final answer. All right, what are we going to say? There are, I forgot them already, 1,500 A seats, 4,500 B seats. I'm still going to run out of room. And I forgot what it was. 17, was it? 17,000 lawn seats? Yeah. So 17,000 lawn seats. Whew. Man, that's a big one. There's a lot going on there. Obviously, if you're kind of skipping around in the notes and you just jump right here, you see all this scrolling and all these notes, and yeah, that's kind of a beast. Define your variables. So that's kind of the process. Like I said, I know every word problem kind of has its own feel to it, but basically, the similarities are going to be there are three unknown, whether it's costs or unknown quantities. There's going to be three unknowns, which we'll define. I'm asking you to define. You're going to come up with three different ways that you can relate those variables, whether it's all three or whether it's just maybe two of them. And then you've got your system. You'll solve it using those same processes that we talked about earlier. Okay, so substitution or elimination. So there we go, checking it off. So I think we're okay here. We've gone through solving all the different algebraic methods, and then we looked at one. Solving a real life, but we kind of gave some general guidelines as far as the process there. So there you have it. Lesson 1.4, solving linear systems, really in three variables, it could say. So there's our notes. I look forward to seeing and hearing from you in future lessons.